Hello, students, and we're going to continue our conversations about acids and bases. And today we're going to venture a little bit further. We've been dealing with the pH scale and how to calculate the pH of something if you know the concentrations of your hydroxide or hydronium ions, and how to transfer in between the pH scale and the pOH scale. What we're going to learn now is something related to our previous chapter. When we dealt with equilibrium, we dealt with equilibrium constants and calculating those and kind of figuring out what does that mean, what does that tell us, if you have a high value for K or if you have a low value for K, what does that mean? And we're going to apply that to acids and bases. So specifically, a reaction where you have an acid being dissolved in a let's say water, or a base being dissolved in water, in that kind of solution. What does that tell you? Before that, though, we want to kind of wrap up something key dealing with acids and bases, and that is we want to talk about something called indicators. And you guys have probably all had some experience with indicators in some previous science class, whether it's biology, whether it's some physical science classes in middle school, or even maybe a beginning chemistry class in middle school, something like that, where you played around with, some kind of indicator. Maybe it was litmus paper, maybe it was purple cabbage juice, and you had a bunch of different substances, and depending what the substance was, it changed a certain color, telling you whether it was an acid or a base. So we want to kind of define what an indicator is. And we won't go into, obviously, a lot of dealing with what indicators are and how they work. Some of that is experiential, so we will have a lab where we kind of do some of this in class. But right now, let's kind of just wrap our minds around what they are. Okay, an indicator is simply a substance that changes color when the pH of a solution changes. And there's quite a few of them. Your book lists a few of them on page 412. I do want you to actually know a few of them. So I would advise memorizing a few there. If you look at that top chart on page 412, it mentions a few of them, like phenolphthalein, methyl violet, thymol blue, methyl orange, litmus paper, methyl red, thymol blue. Okay, purple cabbage juice can be used, red cabbage. Sometimes what it's called, I like to call it purple, whatever. You can use other fruits that can change as well. They list some there. And all of those, the purpose is when the pH changes, you can use those as an indicator. And the one thing to know about indicators is if you look at some of the charts, if you're looking on page 412 there and kind of following along, they don't work for everything. Okay, so let's say I had a certain indicator. It might show me that something is a base, but it might not tell me that something is an acid. And it may change colors over, let's say the range of between 7 and 14. So it might, from 8 to 9, it might change colors, or then when it goes from 9 to 11, there might be another change of colors or something like that. So it's over a certain range, but anything below 7, it doesn't change colors for. Or it could be vice versa, that it'll change colors for acids, but it won't change colors for a base. Or in some cases, all it will tell you is that it's an acid or a base, but what the exact pH is of that acid or base, it might not be as specific. Okay, so it varies from indicator to indicator. And sometimes in the past, you used to have to use multiple indicators to kind of figure that out. Basically, what they do is they give rough estimates of the pH value. I have a couple that we'll use or give examples of that can tell you approximately, this is about a pH of 2, or this is a pH of 11, or whatever it might be. But they're not going to tell you exact. You can even use several indicators together that change colors over different ranges to kind of narrow it down. That's another way to do it. The nice thing with modern technology is we do have what are called pH meters that we can dip into. It's basically a sensor that you can dip into a solution. It will measure the concentration of the hydronium ions. just like, and then it will calculate the pH based off of that, just like we've been doing in class, and it will give you a little bit more precise measurement of the pH value. So that's kind of what an indicator does, and we'll look at some of those in class and how they're used. And they can be kind of cool. And matter of fact, if you have a pool, you probably use some of those on a regular basis. Okay, and so they are used in everyday life for certain situations. What we really want to focus in on today, and we'll spend most of our time talking about, is acid and base strength. Just because you know the pH value does not necessarily mean that you know the strength. That deals more with its concentration. What is the actual concentration of hydronium or hydroxide ions? Now, there can be a relationship there. Generally speaking, stronger acids and stronger bases have a greater concentration of either hydronium or hydroxide ions. Acids would have what ion? That's right, hydronium ions. And bases would have what ion? That's right, hydroxide ions. Okay, and so typically speaking, a strong acid or strong base will have a stronger concentration or higher concentration, meaning it will usually have a higher pH, typically speaking. But I could take a normally strong acid, okay, something, let's say, like hydrochloric acid, and I could dilute it down enough where I could change its pH along the way. Does that mean it's not a strong acid anymore? Not necessarily. Okay, the acid itself per se is strong. It's just that it's diluted down. So sometimes the pH is not necessarily an indicator of whether you have a strong acid or strong base. It's more an indication of what the concentration of your ions is in there. And like I said, there is a relationship. So let's take a look at a few things here. First thing is pH describes the concentration of a solution. It does not describe the strength. Make sure that you understand that. That is an important concept to wrap your minds around. Okay, so what does tell you that something is strong acid or a strong base? Here's a very key concept. By the way, that's a hint. Okay, this is something I would want you to know. This is important. Strong acids give up their protons easily and ionize completely. That's kind of the key thought there, that ionize completely. Weak acids do not ionize completely. So if I was to ask you, what do strong acids do? Well, they will ionize completely. What does that mean? Okay, well, we'll kind of take a look at that in a minute or two. But if you remember our definition, that what is an acid? It's something that gives off a proton. Or what is a base? It's something that can receive a proton. That's that Bronsted-Lowry definition of acid and base. And so what we're saying is, if it's a strong acid, then it's going to do that readily. It's going to give off those protons easily. So when I put that acid in a water, let's say, it'll ionize very quickly. And almost all of your acid will ionize. In other words, it will separate into its different ions. And we'll look at what ions here in just a second. Strong bases, on the other hand, accept protons readily, and they also ionize completely. Okay, they just form a different ion. And weak bases are poor proton acceptors and do not ionize completely. Okay, so the key thing for both strong acids and strong bases is if they are strong, they're going to ionize completely. In other words, break into their separate ions. That's the key, which will lead to a stronger concentration of, generally speaking, of hydronium or hydroxide ions. So let's kind of take a look at this. How do we kind of demonstrate this visually or calculate this? Well, here's what you have, what's called your acid dissociation constant. And if you look there at the very bottom thing, the formula there, kind of looks familiar. That's because it is. It's an equilibrium constant for an acidic reaction. So if I was to do that, and let me get my little laser pointer here. If I was to do that, okay, here is water, and here is my acid. Now again, this is just a fake acid. That's why we have the A here, okay, just to say it's an acid. So you have 8, and the reason we have an H is because that's how you identify acids. That's that proton out front. All acids have that hydrogen. Okay, so I'm putting my acid here into my water. And the reaction is, what does that lead to? Hydronium ion. Okay, so there's my ion. Remember, it's going to ionize completely. Okay, so here's my hydronium ion. And then, okay, what's my other ion? Well, this hydrogen ion here is going to go over to the water. That's where I get my hydronium from. What am I left with? Okay, remember this hydrogen here is positive, so it goes over here. That's why the hydronium is positive. And then the A, the acid, okay, part is going to be left as a negative. Basically, what you're doing is this is your conjugate acid, this is your conjugate base. Okay, so that completes the chemical equation. So I come down here to my equilibrium constant, and so it's products over reactants, you'll notice. And we dropped off the H2O. Why did we do that? Because it's a solvent. Remember, solvents are defined as 1, so we dropped it out. And so from there, here's our equilibrium constant that we write. Okay, it's always going to be the concentration of your hydronium ions times your conjugate base over your conjugate acid. Okay, so hydronium times conjugate base over conjugate acid. Okay, that's always how you will write your, it doesn't matter what acid you're using, that is always how you will write your acid dissociation constant. It's very consistent. Now, what does this mean? If we were to actually plug numbers in here, and we're not, but if we were to actually do that, here's how we would figure out, is an acid strong or not? Okay, remember what we just said. If it's strong, what will it do? Ionize completely. It's going to ionize completely. Well, where's your ions? They're over here, okay, on the chemical reaction. They're on the product side. And so, where are my products and my equilibrium constant? Up top. Okay, so if it ionizes completely, what we're saying is we have a lot of these, a high concentration of ions. So when this acid is put into this water, it ionizes, okay, almost all of it. And so I have a high concentration. So my numbers here in this equation would be large if it's a strong acid. And my number down here, okay, on the bottom, my reactant side, I would have almost none left. And so it would be a very small number. So if I was to go ahead and do the math and calculate this out, if I had large numbers up here, small number here, then I would get a large equilibrium constant, okay, and a number above 1, okay, and that number can end up being very, very large. And what that would tell me is that this is a strong acid. Most of it has ionized completely. If I had a large number down here, in other words, most of it was still reactant, very little became ions, in other words, most of it did not ionize, then that would tell me, okay, I would end up with a small number, a number below 1, okay, a decimal, and that would tell me that I have a weak acid, because most of it doesn't ionize. Most of it remains as an acid. It does not break apart in the solution. And you have a very similar thing, so we'll wave bye-bye to our acids. You have a very similar thing to our bases here. This is a base dissociation constant, and you notice it's called K sub B. The acid dissociation constant was K sub A. And here you have your chemical equation, B for base, mixing it with water. What does that yield? Hydroxide ion, okay? Because the water is going to take one of these hydrogens and leave it over here with the base. And so you have your two ions, hydroxide, and your conjugate acid of this base over here. And so what do we end up with? If we have our equilibrium constant, we have this right here. And again, the same thing. If I have if most of it ionizes, I'm going to have large numbers up here in the product side and a small number down here. And so I will end up with a large value for K. What does that mean? It means most of it ionizes, therefore it's a strong base. If I end up with a small number, okay, for K, because I have a small amount here and a small amount here and a large amount down here, so I end up with a decimal, that tells me that I have a weak base because most of it did not ionize. Okay, that's the key thing as to telling whether something is a strong acid or a strong base, is whether it ionizes completely.